going to start with an example of applied probability. So I am the third coach on my son's baseball team. It's grades 7 to 10. I am the analytics guy. And the league has some rules which, if you understand math, you can exploit. You cannot start a new batter if it would be your 76th pitch of the weekend. So there is a limit to how much we want the little kids to throw. And there are some teams that only have one strong pitch, and after that they have a really weak bullpen. And so what I have finally been able to convince some of the batters and the coaches to do is do not swing on the first pitch if the umpire has a really bad strike zone. Wait until you get a strike, try to really work up the pitch count. We lost a heartbreaker 2-0 on Saturday, where their pitcher started the final inning having thrown 73 pitches. So told the batter, do not swing on the first pitch. All we have to avoid is a one-pitch pop-out. Because if he has to throw 2 to you, he can't start a new batter. Yes, coach. And the head coach told him this. Yes, coach. And what do you think he did on the first pitch? Swung and popped up to the catcher. And so that meant that their pitcher could face 2 batters, got 2 outs against us that inning. We then rallied. We had multiple people on base, but with 2 outs, one of our batters struck out on a bad called third strike, and the game ended. But this could have been a shining moment for analytics. The next day, we implemented this a little bit earlier and a little bit more vigorously, and we actually knocked out their starting pitcher in the 5th inning, not in the 6th. And the small little trickle effects. So when you're trying to calculate these things, what are these probabilities? Well, what's the probability that the first pitch is going to be a ball? If it's a ball, then taking it is not bad, and it starts to give you a favorable count. And in fact, one of our batters, by being patient and not swinging until he got that first strike, he ended up getting a 3-1 pitch, which was a nice marshmallow down the middle. And I was like, come on, everybody, it's going to be a marshmallow. And it was a marshmallow, and he just belted into the outfield. And so it was a nice example, and you don't always get this, where you can actually show people in real time the power of mathematics. Most of the time, it's like, yeah. And too often, the theorists do not really take into account the players. But if you can look at the probabilities of events and see what is the harm in waiting a little bit, it often turns out it's actually not that bad. It's actually, the risk is not large. Let's take the chance. All right, so what we're going to do now is we're going to do chapters 7 and 8. So this is discrete and continuous random variables. Essentially, the main difference between the two is discrete uses sums, continuous uses integrals. Notationally, what you can then do is you can overload the integral sign and have the integral sign often also mean sum or even a mixed sum and integral. You might have seen stuff like this where your absolute value of -3 is 3. And then the length of the vector 1, 2, well, let's do better 1. Let's do 3, 4. What would be the length of that vector? 5. Okay? And so this is just using the norm of the vector. Well, a lot of people say, screw that, let's just write and overload the absolute value sign and do this for the length of a vector. So it's sometimes nice to just overload notation so you don't have to write things up differently each time. I will often either do things always for the integrals, or maybe I'll try to alternate and do things for the integrals and the sums. I'm not going to do things for both of them because it's essentially the same argument. There are some small differences between the two in terms of values of the densities, and that will be a little bit interesting. So a density has several properties. So we might do f sub x, we might do f, we might do p. We have a lot of different ways of writing what we want our density to be. If we have multiple random variables in play, I like putting the subscript x because that's going to remind me this is the density associated to x. So can somebody tell me a property we want a density to have? What should its values be, for instance?
Between 0 and 1.
Okay. I am glad you said that. You are half right. If it's discrete, it's between 0 and 1. All we know is that it has to be greater than or equal to 0. What's the so I'm glad you said that. We will circle back to that in a moment. What's the other condition we want? So it has to be non-negative. And what else do we want?
Less than x.
Not less than x. So this is supposed to be the probability. So if we look at the probability of the whole space, what would the probability of the whole space be? 1. So we could write that as an integral, the integral from minus infinity to infinity of fx of x dx equals 1, or the sum of fx of, say, xn equals 1. And we always assume if it's discrete that we have at most a countable infinite number of objects. Things that are in a one-to-one correspondence with the natural numbers, and if you want the natural numbers to include 0 or not, I'm fine either way. This is the area under the curve. And in 3, we'll frequently say that the probability that, say, a less equal to x less equal to b would be the integral from a to b of the density. It's the area under the curve. How do you evaluate integrals? What technique do you use? What theorem do you use? Yeah, how would you evaluate this integral? You would want to find the what?
Antiderivative.
The antiderivative, or the integral. So you find big f of x such that its derivative is little f of x. Now, I went to the Ohio State University for a year as a postdoc. Yet again, we beat up on a weak team. This is not a situation for the. This is a situation for a. Is there a unique antiderivative? If I give you a function, does it have a unique antiderivative? Or if there's more than one antiderivative, how do they differ?
The constant.
The constant. And in fact, we look at big fx of b minus big fx of a. So if I add 5 to the function, I'm going to add 5 and then I'm going to subtract 5. It's unchanged. How many of you have taken physics? Okay. Do you ever do experiments like this? You don't want to waste chalk here. Okay? And you look at the change in energy. You've got the potential energy. You've got the kinetic energy. You have the law of conservation of energy. And then where is the potential energy defined? Is it defined from the floor? Is it defined from the ceiling, from the center of the earth? You have lots of different places to choose where you define zero potential energy to be. It doesn't matter, because in all the problems you look at, you never have the potential energy floating by itself. It's always change in potential and change in kinetic. So it's the same thing here. We don't really care which antiderivative we take. How many of you have taken Calc 2? So I've actually never taught Calc 2, and my goal is to go through my entire career without doing it because it's been so long. I've done Calc 1, I've done Calc 3, I don't ever want to do Calc 2. I did substitute for one professor for one day in Calc 2, but they were doing Calc 3 material, so I thought it was okay. What do you learn in Calc 2? What techniques do you learn? Integration. So what is your favorite integration techniques? What do you like? So what kind of integration techniques do we have? There are some that you don't like. We've already talked about partial fractions. I won't give you partial fractions. I won't give you trig substitution. Okay? Those are off the table. You now need to give me 2 integration techniques that you like, or I will bring those back into the exams. Okay? Give me an integration technique. U substitution. That's good. Give me one more technique or I bring back partial fractions. Integration by parts. Good. So integration by parts and U substitution, fair game. Trig substitution and partial fractions are not. Okay? Now, Calc 2 I call the calculus class of lies. When you leave that class, you leave believing that you know how to integrate. You don't. Just so you feel better, the 2 professors in this room also do not know how to integrate. Right? It's very fortunate that there's a lot of functions that are close to things in the real world that have nice forms, that have nice antiderivatives. But most functions do not have a nice antiderivative. Most of the time you have to resort to numeric techniques. Later in the semester we will actually do Monte Carlo integration, where essentially you take a dartboard and you throw darts at it and you find the values of integrals like this. And if you think this is scary, this is how a lot of financial integrals were done for many years. It's actually a good technique. It's a nice application of the central limit theorem. Some people call the series of papers on this the most important papers in 20th century mathematics because of how many difficult problems there are that can now be approximated well with techniques like this. It's important to understand what you can and cannot do. Everyone has taken a class on integration? Has anyone taken an advanced summation class? And this is why typically the discrete case is harder. We don't have as many nice formulas for sums as we do for integrals. And this is why we love to resort to integrals whenever possible. Now there are a few differences. So earlier you had made the great comment that the density must be between 0 and 1. It's the probabilities of events that must be between 0 and 1. So in the discrete setting, each of these probabilities must be between 0 and 1. But in the continuous setting, all I need is the integral to be 1. Is it possible that maybe the function is larger than 1 in some places? Could the function be as large as 20? Over how large of a region? At most?
1/20.
At most 1/20th. Could the function be as large as a googolplex? Yes, over a region at most of size 1 over a googolplex. So a function can be extremely large at small points. It can be extremely large in small intervals. And in the continuous setting, we actually don't have an upper bound on how large the density can be. In the discrete setting, we do, and it cannot be too large. And I've mentioned this before. Whenever you talk about the fundamental theorem of calculus, which is what we use to calculate these, it's not the fundamental definition of calculus. Right? The content is that this expression here represents the area under the curve. If I give you some function like this, and here's A, here's B, it's the area under the curve from A to B. And the fundamental theorem of calculus says that it is the antiderivative at B minus the antiderivative at A. If you don't say area, then there's no content here. If you want to make me mad, drop area. Okay? Rooting for the Yankees, slightly worse. Only slightly. Okay? Do not drop the word area. And again, this is why we care so much about calculus. You've spent all this time taking these math classes. There should be a reason, right? We're trying to develop tools and techniques that you can use to tackle a variety of problems. Calculus can be used for many things. So what I want to do now is I want to do a cookbook problem. I'm going to give you f of x, because I think I want 2 minus 3x, no, 2 plus 3x, minus 5x squared, 0 less than equal to x less than equal to 1. And this function will be 0 everywhere else. So the question is this a density? So what do we need to check? We need to check and see if it is. We don't need to say it's continuous. It would be nice if it was continuous, but you can still be a density if you're not continuous.
I guess we can work through the conditions.
We can work through the conditions.
Check it.
So is it non-negative? So you could try to plot this. And if you plot this, you will see that it's non-negative. You can also try to do some algebraic analysis. There's lots of ways you can do it. What's f of 0? 2. What's f of 1? I'm risking this part of the lecture. When I was young, this was still included in the calculus curriculum. I don't know if it's included in yours. It's a good technique to know. What's f prime of x? 3 minus 10x. F prime of x equals 0 implies x is equal to 0.3. Have you ever seen plotting functions like this? Okay, I saw 1 yes. That's more than I was expecting. Excellent. So here's 0, here's 1. We know at 0 the function is 2. We know at 1 the function is 0. 3/10 is also an important point. Let's look at the derivative. At 0.3, the derivative is 0. If x is less than 0.3, what can you say about the derivative? So if x is less than 0.3, is the derivative positive or negative? Positive. If x is, there you go. That's what a professor loves to see. Right? And a smile, I got both. What if x is greater than 0.3? What can you say about the derivative? Negative. So the derivative actually gives us information. If the first derivative is positive, the function's increasing. If the first derivative is negative, the function's decreasing. So I can do some curve sketching. I know it's 2 at 0, I know it's 1, I know it's increasing up to here and then decreasing. It's going to look something like that. And that's now a proof that it doesn't dip down anywhere. You know, it's unlikely that it would come back up so quickly like that. But here's the proof now. So this quickly proves that the function is non-negative in the region we care about. And this is a wonderful application of the first derivative. If I wanted to draw it better, what else could I look at? Yeah, I don't want to draw it better. This is the 21st century. We've got computers that can do stuff like this, okay? You know, it's not bad that most of this has been removed from the calculus curriculum, but the shame of it is you sometimes lose the ability to do quick arguments like this and get a quick sense of what is the behavior. And again, this is a toy problem. This is not a hard problem to understand. But there will be harder problems where being able to do a quick sketch like this is useful. Now here's another thing you can do. 0 less than equal to x less than equal to 1 implies 0 less than equal to x squared less than equal to x less than equal to 1. If your number's between 0 and 1, if you square it, it's going to be smaller unless you're 0 or 1. So that means if we look at 2 plus 3x minus 5x squared, that's going to be less than equal to 2 plus 3x minus 5x. This is equal to 2 minus 2x. What is this screaming at you to do? You've got 2 minus 2x, what should we do?
Isn't the same thing?
What's that? Yeah, pull out the 2. And now this is clearly going to be non-negative in the region. You know, we've got 2 times 1 minus x. So this is going to be, oh, did I put this the wrong way? Oh yeah, I'm sorry. Yes, I have negative x squared, so it goes this way, sorry. I drew it the wrong way. Is that what you were? Okay. Because x squared is less than equal to x, negative x squared is greater than equal to negative x. So when I replace the negative 5x squared with negative 5x, I've decreased the value. And if it's still positive after doing this, then the original thing had to be positive. And so this will be greater than equal to 0. Okay, so it satisfies condition 1. Do you think it satisfies condition 2? Do you think it integrates to 1? What are your thoughts? Or what could we do if you're afraid to guess?
Just try. Integrate it.
Yeah, just integrate it. So let's integrate from 0 to 1 of 2 plus 3x minus 5x squared dx. So this is integral from 0 to 1 of 2 dx plus, I'll call it 2 maybe, plus maybe 3 integral from 0 to 1 of x dx minus 5 integral from 0 to 1 of x squared dx. You do not need to break it up into this many steps. If your integration is comfortable, go fast. So this would just be 2x evaluated at 0 and 1 plus 3x squared over 2 evaluated at 0 and 1 minus 5x cubed evaluated at 0 and 1. Life is good. We're only evaluating things at 0 and 1. This is not a coincidence. I'm the one who has to do this at the board. So you get 2
Would it have a divided
by 3, yes. Thank you. So we get a 2, we get a plus 3 halves, and we get a minus 5 thirds. So the common denominator is 6. So if we multiply this, we would get 12 plus 9 minus 10 over 6. And that would be 11/6. All right, at this point, it's quite clear that it does not integrate to 1. Life is not always perfect. It's not a distribution. If you had to violate a property, which would you rather violate? The integral is not 1, or the function is negative at some points. I'm sorry?
Before.
Yeah, I would much rather violate that the integral is not 1. I can fix the integral is not 1 without too much trouble. Right? What do we need to do? Yeah.
We multiply the whole thing by 6.
Yeah, just multiply the whole thing by 6 11ths. Right? So the new and improved function, g of x, is 6 11ths f of x. And this is the theory of renormalization. So if you have to violate one of them, question?
So do we just have that second condition so we renormalize?
No, it's just you need to assign an area of 1, a probability of 1 to everything. If you assign less or more, we can just rescale the function by a constant, and then the new thing will work. So really what we're doing is we're sending f of x to the following new function. F of x, and then we divide by the integral from minus infinity to infinity of f of x dx. Or sometimes people would be like an f of t dt, just so you don't see the same variable twice. Even though we integrate out the variable over here, so it doesn't really matter. If my function is non-negative, this will always integrate to 1. And so for a lot of problems, it is amazing how powerful this is. So how many of you have seen chi-squared random variables? Only very few hands went up. So these are extremely important in statistics. They're extremely important in error analysis. It turns out we can prove a lot of the results we need about chi-squared random variables by just looking at the functional dependence and saying, well, look, the following has the same functional dependence as a chi-squared random variable, but we don't know what its normalization constant is. Well, the normalization constant has to be the same because it has to integrate to 1. As a consequence of this, we will get for free some very interesting results. Anybody know what the area of a circle is? So that's the area. What's the perimeter? What's the volume of a sphere?
4/3 pi.
4/3 pi r cubed. What is the surface area?
4 pi r squared.
Do you notice anything about these numbers? Pi r squared and 2 pi r. What's the connection? Derivative. 4/3 pi r cubed and 4 pi r squared. What's the connection? So if you just remember the derivative connection, you only have to remember half of the formulas. That's a 50% memory savings. Okay? Now, area is r squared, volume is r cubed. If we did the hypervolume of a 4-dimensional sphere, what do you think you would have? Yeah, an r to the 4th. And then the question is, well, what would be the constant? And the constant involves pi to either integer or half integer powers. It involves the gamma function. And it turns out you get all of that for free from the theory of renormalization applied to chi-squared random variables. We will see this later. It's called integration without integrating. Because it's a probability distribution. What must it integrate to? 1. So if you can recognize the functional form, then you get the normalization constant for free. I got a bunch of messy stuff, and it's got to work out. So I don't even have to evaluate it. I can just keep it floating around, and then at the end of the day, it all has to align.
Why don't they teach this to us in middle school?
Well, most middle school kids haven't seen differentiation. But once you get to a calculus class, once you get to high school, you can easily say this. So I'm willing to say this with the camera rolling, we do not have nearly enough time for me to talk about things that are done wrong in high school. I am happy to have a lunch and discuss this. Actually, it would probably be a series of lunches, plus several coffees and a few banging your head against the wall sessions. I will just say that I know the camera's rolling. Did I tell you the story of my brother and his master's in education? He was an engineer at Georgia Tech. He went off to Silicon Valley, did very well, but got fed up, burnt out, decided to get a master's in education. My parents reside in Tucson now, they've retired. He says, I'm going to get a master's in education, I'm going to apply to the University of Arizona, it's near my parents. He gets in, but they tell him, before you start, you have to fix your math deficiency. He goes, my what? You're 1 math credit shy. He goes, well, here's my transcript. What do you mean I'm shy? He goes, well, yeah, it doesn't say math, it says EE. What? So all the advanced communication theory classes, all the advanced story analysis classes he took in engineering did not count. He said, I essentially taught multivariable calculus. And they go, well, it doesn't say math. There's a little box. We need to put a check mark in the box, and we can't with what you have. You have to fill the requirement. You have to make up your deficiency. Okay, well, what do I need to do? You need to take algebra. How many of you have taken algebra in college? Actually, I haven't. It never fit to my schedule. How do you take an abstract algebra? How many of you are planning on someday taking abstract algebra? All right. They weren't talking about abstract algebra. They were talking about high school algebra. And before they let my brother, with a degree in engineering and years experience in Silicon Valley, before they let him enroll, he had to take an algebra class, a high school algebra class that he couldn't place out of. Finally, halfway through the semester, the teacher said, gee, it seems like you know the material. And so there are many, many, many inefficiencies that we have no control over. I agree that there's a lot of things that should be talked about. We did TaylorSeries in this class, right? Oh no, that was operations research. I'll try to work that in. There's a way to bypass multivariable TaylorSeries with the Hessians and all the mixed partial derivatives and get it for free from just one variable calculus. And so remind me at some point when we have a few minutes at the end of a class one day when we're trying to fill up some time, and I will put something like that in. Or maybe I'll try to leave a little bit of time here and do things a little bit differently. Yeah, so I'm going to skip then the die problem. I'll just summarize it very briefly. So this is not about people whose health is in bad shape, it's about rolling die, okay? So we've all hopefully seen this. You have a die numbered 1 through 6, you roll it, you can roll 2 fair die, 3 fair die, etc., and you can look at the sum. And you can calculate what is the probability, maybe x1 plus x2 equals n. And you'll get 2 less than equal to n, less than equal to 12, and you can just enumerate all the pairs. And if you actually write it down, the number of pairs is going to look like a triangle. You're going to have just 1, 1 to get a sum of 2, and just 6, 6 to get a sum of 12. And then to get the sum of 7, you could have 1, 6, 2, 5, all the way down to 6, 1. And we saw this triangle pattern before when we looked at the sum of 2 uniforms, and we saw what happened as we added more and more and more. All right. We've talked a little bit about moments. So the kth moment is the integral from minus infinity to infinity of x to the k times the density dx. And we sometimes write this as e for the expected value of the kth power. You've seen several moments before. You've seen the first moment is the mean, the second moment is related to the variance, the third and the fourth moments are related to the skewness and the kurtosis. Most of the time, we don't really care about the skewness and the kurtosis. For most applications, the first 2 moments is fine. The only situation I've ever seen is that I think I told you when I visited my friend at Harvard, and they listed the first 4 moments of the scores of the pre-med class so that all the concerned Harvard students would know exactly how they fared relative to everyone else. The hope is that the more moments you know, the more you know about the distribution. And if you know all the moments, then you know the distribution. So this is similar to a hope you might have from calculus, that if you know all the Taylor coefficients, you know the function. So for instance, e to the x is the sum, n goes from 0 to infinity, of x to the n over n factorial. Cosine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on and so on and so on. And the hope is if you know the Taylor coefficients, you know the function. It turns out that that's false. There are functions that have the same Taylor series but are distinct. And the reason for this is the evil function f of x is equal to e to the negative 1 over x squared if x is not 0, and 0 if x is 0. If you look at this function, it's easy to take the derivative of this function everywhere except at x equals 0. At x equals 0, the only way you can take its derivative is you have to use the definition of the derivative. you have to look at f of h minus f of 0 divided by h. So you go back to the definition of the derivative. So you would have e to the negative 1 over h squared minus 0 divided by h. And then you would use L'Hopital's rule. And when the dust settles, you would get that the first derivative is 0 at 0. And you would have a split definition for the first derivative. To find the second derivative, you would use the definition of the derivative again in L'Hopital's rule, and you would get the second derivative is 0 at 0. And the third derivative is 0 at 0. In fact, every derivative is 0 at 0. So if you try to do a Taylor series where every coefficient is 0, your function becomes identically 0. This function is not identically 0. If you plot it, it really looks like 0 in a neighborhood of the origin. But it's not. This means Taylor series are not unique. And this is a real problem. So when we get to the central limit theorem later in the semester, we are not going to be able to fully prove the central limit theorem. We're going to need some black box results from complex analysis about when can we uniquely determine the distribution. I want you to be aware of where I am going to be a little incomplete, and to give some justification for why you might want to take these advanced math classes. You know, why do we offer classes like real analysis and complex analysis? We need to make stuff like this rigorous. We've seen Russell's paradox, where things seemed very reasonable about how you form sets, and it turns out, no, it's wrong. So we've got to be careful. So sadly, it is not the case that we can always write down a function uniquely from its Taylor series. Because all the Taylor series coefficients of this function at 0 is 0, I could add 1,701 copies of this function to cosine of x, and it wouldn't change the Taylor series at the origin. And that's why it's so bad. All right, any other questions about stuff like this? For the rest of the class, I wanted to do a coding example, but since I'm going to switch to the laptop, what I think I'll do is I'll do a quick Taylor series expansion and teach you how to do multivariable Taylor series without doing multivariable calculus. So cosine x squared plus xy. Okay, let's say for some reason we wanted to expand this. So we start taking the partial derivative with respect to x, the partial derivative with respect to y, two partial derivatives with respect to x, two partial derivatives with respect to y, then a partial derivative with respect to x and a partial derivative with respect to y, and we start filling that out, and then we start going, oh crap, now where does the 1 over 2 factorial go, and when I have the cross terms, how often does this sound vaguely familiar? Does anybody have fond memories of this? Okay, so no one has fond memories of this. But this would be a legitimate question to give you on a Calc 3 final, correct? And you probably might have gotten something like this. Do you want to see how to do this using Calc 1? What's the Taylor series of cosine of u? 1 minus u squared over 2 factorial plus u to the 4th over 4 factorial plus dot dot dot. Let u equal what?
X squared plus x.
And now you get the cosine of x squared plus xy is 1 minus x squared plus xy over 2 factorial plus x squared plus xy to the 4th over 4 factorial, and so on and so on and so on. I'm sorry?
Is the second term?
Oh yes, this should be squared. Thank you. Boom, we're done. If I changed it to y squared, is that a big deal? Oh. Not a big deal at all. It's trivial. Now, if I do change it to y squared, life is painful. And the reason life is painful is x squared is a degree 2 term. xy squared is degree 3. So when I expand this out and I square it, I'll have a degree 4 term, a degree 5 term, and a degree 6 term. When I expand this out, I'll have a degree 8 term all the way up to, okay. But now the danger is that different terms could interact. And if you want a Taylor series of degree 3 or 4 or 5, you might have some later terms coming in because of the degrees. Not a big deal. You know, it bypasses the need to do all this multivariable calculus. So how many people have seen this trick before, out of curiosity? So it's amazing which tricks you see and which tricks you don't see. Have you seen the tricks from finding the determinant of a 3 by 3 matrix with the pluses and the minuses?
Oh, I think I saw that.
Yeah, where you go diagonally like this, and you put down the first two columns again. So there's a lot of things you can do to make your life easier. A lot of times you can almost remember a formula, and if you can almost remember the formula, that's often enough. So now that we've talked about how the derivative of a sphere's volume is its surface area, if you can remember the volume, you can get the surface area, or the surface area, you can get the volume. As a nice homework problem, think about why that's true, or as an extra credit. Why should we have the derivative of the area gives us the perimeter? Why should we have the derivative of the volume gives us the surface area? All right, any other theoretical questions now before we shift to programming? Okay.